Okay. So the next example is the Sudoku. And basically the idea is to parallelize the Sudoku. So it solves the 49,000. Yes, I'm using Beam. And actually I have some problems with my setup, but yeah. For example, is a bit broken, but anyway. Oh, now it works. Human false, but I don't remember if I care about it. Oh, it's not the. It's not it's a band again. Okay, so the Sudoku. Yeah, a puzzle game looks like that. Okay, so this is basically how to parallelize a Sudoku solver, and it says quite fast. Can solve 49,000 of the 17 clue puzzles. So puzzles with 17 clues. The known ones like around 2 minutes, so it's quite fast. And the idea is to parallelize it. Okay, so let's start take a look about that. I copy the Sudoku stuff already. Yeah, so this is the solver. We take a look at this. So the solve is quite simple. It takes a string and returns maybe grid, where probably nothing hasn't been solved and maybe just it's a solution. And then we have the code of doc1. That's 2. The only functional programming language I know is. Well, you can do like different. What do you mean like looks native? I guess you can do like functional programming, right? Okay. Okay, interactive with the US. I'm not sure like fully what you mean. I mean, I would say that C is more native or low level. I don't know. So in that sense, Haskell is much higher level. Although you can do low level, but normally it's used for high level stuff. And one of the things that in the book the author mentions is that basically, there are quite some instructions that you can do, and the runtime of the language provides some instructions for you to handle, in this case, concurrence and parallelism. So, okay. yeah, that. So this is the oh, actually, so to the Sudoku thing. Yes, that's right. In that sense, you are totally right. So Haskell syntax, it's completely different, and it's one of the things that if you come from C family of languages, it's different. Although I wouldn't say that Python is a bit closer because it's also white space based and not like with brackets. But yeah, the syntax is different. But no problem. So it's something that it doesn't take too long to get used to. There are other things in the language that probably are more, yeah, take longer time. So let's remove this. So yes, give me a second to paste this and I can explain a bit what is happening there. Par one. Bam. Par. Yeah, so there's one here. Actually not. So it's actually not a function, but just like expression. You will say this do thing. It's a way of writing more like sequential or imperative code, as you would write in C. And it's actually a syntax sugar to a sequence of or a chain of operations. So what's happening here is that no, not like go to, but basically each line in this what is called do block is doing a sequence of operations, and you could write them without the syntax sugar be some guy. I guess it will be, yeah. It describes a sequence of operation. That's a good word for it. And in this case, is for evaluating things either in parallel or sequentially. Yeah, it's quite weird because it's not a statement oriented, but just expression oriented, and then this do here, it's kind of like it allows you to write code in a way that looks like it's statement oriented, where you have each line doing some operation, but actually it's still a series of expressions that get evaluated sequentially. So in main, we go back to say Sudoku 1. Okay, thank you for joining. Feel free to join again and ask questions. Have a good night. Thank you. Okay, so let's run this again and then try to understand and remember. Nice. Yeah, there is a Discord. Let me find. If you want to join and you want to ask questions there, I guess we will be glad to answer, because I'm sure you have many. I need to add the bot. You're welcome, Rocio. Okay, so yeah, this is just basically what is this doing? One. So maps all the input, which is all the lines in the file, which are each case, and take a look at it. So yes, yeah, so basically these are all the cases, and it's mapping those with the solve. So solution is a list of maybes, and then it just filters the ones that are just and prints the length, and that basically runs all the solution because it's forcing the evaluation. So, but I want to check what the book mentioned about the here. Now I remember. So this is the total time that it took, 11 seconds. That's about running the okay. Anyway, lapsed. So I'm just checking what the output means. So and this is not running one core. Can you run one core and one core? Yes, there we go. So now total and elapsed, which says here. Okay, elapsed is the total is the total CPU used by the program, and the elapsed or work clock time. Okay. Okay, so this is when it runs in one core. Why does it take longer to run threaded? Weird. We have the first implementation that runs parallel, or that adds parallelism. Sec A. No cradle for okay, without formatting. Okay. Actually, I should leave those because they were notes from the book. Okay, so what does it do now? So one was just running the exercise, and Sudoku 2 okay, so we split. So what is it doing? Puzzles are just all the puzzles, and then it splits the puzzles too. So we have a list of puzzles and a list of puzzles, and then uses force. And something, so let me go back in a second. It solves each one in parallel, and then it waits for each solution, and then it appends both. So one. Okay. So if we compare with the weird part that I'm running in parallel and it's taking way longer. Maybe of course. Okay, so with one core it takes 1.6 seconds, and with two cores it takes 1 second. I need to figure out why running with like no constraint takes even longer. Just so weird. Yeah, here it explains. Here we get the second one. So yeah, we split into two parts, and then we just do which was the one. Very productive, 50%. Yes, I don't know what's up with running with all the cores. So yeah, it's doing this version now. First with 4 volts in parallel, so the evaluations start in parallel, and then we wait for both of them and we return. So I think it makes more sense to either run with 2 cores, so it takes around 1 second, or with 1 core, then it takes 1.6 seconds. So it doesn't speed double when you add 2 cores, because I think I'm guessing why it's running longer, but I'll need to double check that. But yeah, so it cannot speed double because there is, of course, things that don't run in parallel, and then there is the overhead of parallelizing things, but still it improves. Okay, so now let's produce this output. I need to build with event log. I need to build. Okay, so this is going to, we are just going to take a look at the and log and RT is oops. Oops. What? Event log. Great. Maybe I cannot use a stack runner one. So this is to generate the output for hope. The program to take a look at the concurrency. Sorry, profiling parallel programs. But for some reason it does not want to. No, I think I see what it does. I think I need to compile again, but like I need to remove the predator and log RTS. No. I think it shows the same, so I need to, yes, that thing. Now nice. So now we have the event log file. Let's go. Are there? Okay. Good look. See. That worked. But basically it shows pretty much the same. Yeah, this is cool. So what we see here is the activity, and these are the two cores, and we see that eventually one stops the other. So we have a lot of time here that the core wasn't doing anything. One core. So, and I think this is similar here. Yeah, so then the book goes and explains that you need to find a way to split into the smallest chunks, because we split in 2 chunks, but the solutions were not. I think that even the file is generated in a way where one of the halves takes longer to calculate than the other, so we see this even like more. Yeah, it shows more the difference between two of the types. So I think we have Sudoku 3, yes. And this looks quite similar to the first one. 3. Okay, so now they define, the author defines parallel map, and let's see, map first. Add it here. Our map takes A, B, list of A's, returns value of B, if I'm not mistaken. Yes, that's the right signature, and the base case is the same. But then here we have to A, F, X, bar map up of F, yeah, pure A, A. So this is an ace, not an as, but an ace. Sorry for the bad joke. And I think that's it. And then what we do is we use Parma. Tag build. Parallel. This one has our map, so wrong now. Here. And to print that, need to run the value. Run. Okay, so what's happening now is that we do basically every solution parallel. Let's see how it performs. Let's code. So it didn't improve that much. But it seems like everything is properly split now compared to before. Almost everything. There is some funny here. See what I should get. Okay, so it mentions something interesting. We have sparks here. Why? No, sparks, sorry. So there were 1,000 sparks, and that means that we basically run these 1,000 of these eval. Sparks are the units of work that can be done in parallel, and all of them were converted. None of them were overflown or GC'd or anything, so that's good. So explanation of, yeah, if it's the get garbage collected. Overflow, it's if the pool of sparks gets, yeah, it has a fixed size, so if it gets overflowed, it drops some. Do this or that here. If it's when it's applied to something that was already evaluated, she see it if it's they get garbage collected, and fizzles. Okay, so this is the expression was, this expression was unevaluated at the time that spark was sparked, but was evaluated later, so they are removed from the spark pool. This is interesting. And yeah, so what the author does now is zoomed in. There is a lot of this, and I think this part is fine, but this one, yeah, there's like work, and then there is times where nothing is happening, and then some work. Okay, so this basically, there is a lot of garbage collecting going on, and I guess it's this color. Yes, this color, and it's happening like by one, most of the time by one of the cores. This is because we are splitting the file into lines, and this is kind of lazy, so okay. Because it adds evaluate. Okay. So it mentions so evaluate is similar to sec, but it does it in IO. So it's fun again, but first. Now it does look different. It didn't change much. Like this. Yeah, okay, so it makes sense. There is a part that's sequential. This, and then it executes in parallel, does some garbage here, yeah, some other garbage collection. Fine, it stops here, but nothing happened. Why was that? I wonder what's happening. And then it's sequential at the end. And then this is something interesting. So the author mentions a formula here of how much the speed ups we can get with parallelism. So one guy 1, 2, over 1 9 e over no plus over. So what are these things? How much can have with this? Where n is number of cores. I don't and p is portion of runtime that can and this has a name which is, I don't think I'll try to pronounce it. Amdals and house and the house. So and what does that mean is so then it mentions that the theoretical maximum speed up yeah, so these 16 milliseconds around that we saw at the beginning, this is the part that limits how much the program can speed up, and yeah, no matter how many processors at some point, it's, yeah, you cannot improve anymore. So it is impossible to achieve a speed up of 46, no matter how many cores with that. So the maximum speed up that we can achieve in this case is 1.96 with 2 cores. Okay, I guess that's it for today. 2 hours of stream already. Yeah, I didn't finish the chapter 2. There are some more exercises. We'll take a look at DeepSec next. I need to review this because I tried it. Actually, there is only one more page. Let me take a look. Okay, so there was a force earlier that we saw. Yeah, let me do that part, because there is only one more thing that the program made. So Doku 2, we use this deep sec. We are using only force there. Force fully evaluates x and then returns. Note that force x only performs evaluation when the value of force x itself is 100%. Returns shallow evaluation. Force. Yeah, but if you use NFT data, okay, so it's not for everything. Yeah, basically we define not built-in thing like spec, and well, I don't think it's built-in, but it's based on the NFT data type class. So let's take a look at it. The repo. Yeah, so it implements this R and F, which is translate to reduce to normal form, and it fully evaluates the arguments and then returns. Yeah. And the default implementation is basically sec, so reduce normal form. The default implementation is a sec and total empty. Yeah, for simple things that have yeah, for example, bool can use the default one, but then most of the common types are already implemented. And the idea is simple, so we can implement it for the where we have either nil or not 3. Branch with it, please. Branch b of a, then a, instance of data a. Where reduce normal form of m of int. Sorry, it needs to return unit. And then branch case a is yes, better left. Yes, so left a and right would be So let's use the normal form of L, then sec of the normal form A, sec form of R. Yeah, so the idea is basically recursively evaluate, and this is what was used here. With force. And then there is deepsec. Type sec is basically the same as sec, but yeah, to normal form. Big head. And I think that's it. One thing to mention is that sec here is on, big on, one, sorry, because it only evaluates to the head, whereas deepsec is on because it evaluates the whole structure. Yeah, and then these are kind of like the two ends where you can evaluate the weak head, but then there is things in the middle like length that evaluates only the spine of the list and doesn't evaluate everything. So there is control stack. So if you need like a lot of control when you're evaluating things in parallel, there is control stack with the author mentioned that it's not going to be used in the book, but sequential strategies. This is the one we saw already. So there stack tuple, no. Okay. Okay, so yeah, there are some combinators here. So r deepsec, rsec, sec list n. So the first n elements of the list, evaluate the nth element of the list, and this evaluate the spine until that element. Foldables, map, array bound, tuples. Okay. So that was the chapter 2 of the book. So next week I'll continue with chapter 3 and I'll try to prepare the exercises a bit more. But yeah, that was fun. Thank you for joining. And then the mandatory tweet to wrap up. Thank you everybody. Have a good night or good evening or whatever. Bye bye.